Hello and welcome to this video on the states of matter. Today we're going to talk about solids, liquids, and gases and just some general properties and characteristics of those three things. So grab your notebook and something to write with and let's get started. So the first thing we want to do is we want to know about the kinetic molecular theory. And so basically this is talking about how molecules actually move. And so within the kinetic molecular theory, we can actually understand what's going on with solids, liquids, and gases from a molecular level. So this is kind of the place where we want to go for high school chemistry. So the first thing is that all matter is made up of particles, and so or molecules or some sort of pieces. And those pieces are in constant motion. They are all moving. And so the rate at which they move is going to be characteristic on what type of substance we have. We know that there's this theoretical value called absolute zero where basically all molecular motion stops. Now, scientists have approached very, very close to this number, but they're still trying to get down to absolute zero. They've been so close that we would kind of call it, but we see that up until that point, or by the time we get to that point, everything is still going to be moving. And so there's going to be a place where we actually have a temperature at which things no longer move. But for most of what we see in the real world, all molecules are going to be moving. So as molecular motion increases, we see that there's an increase in thermal energy and or pressure. And so as we see increases in pressure and a lot of times what people would call temperature or thermal energy, we see that the molecular motion will increase, and vice versa. As the pressure drops or as the temperature or thermal energy decreases, we'll see that molecular motion will actually slow down a little bit. And so that's how we actually can define what's going on with our different states of matter, is by taking a look at how these different molecules are moving during their different states of matter. So we measure these values, and one of the ways that we measure them is by measuring temperature in Kelvin. And so if you remember from earlier in the year, Kelvin is actually equal to the degrees Celsius plus 273. Okay, or degrees Celsius is equal to Kelvin minus 273. And so that's what we're going to be working with quite a bit. So that might be something you want to make sure that you kind of have in the back of your mind. Okay, the other thing that we're really concerned with, as we just talked about, is pressure. And so we haven't dealt with much in the way of pressure. We talk about atmospheres a lot of times. So 1 atmosphere, ATM is atmosphere. Or 760 millimeters of mercury and 101.3 kilopascal. So those are all equal to one another. And the way we actually go about measuring these is by using a barometer. Now, a lot of times we have digital versions of these now, but originally what we had is we have these barometers. And so this is actually, there's mercury that's in down in this pool here. And as the atmospheric pressure pushes down on this, there's a vacuum up top, it actually causes the mercury to get pushed up into here. And so as pressure increases, okay, so as we have greater pressure coming from the atmosphere, we see that that goes up. And so this is at sea level. If we were to go stand on the top of Mount Everest, there's not as much atmosphere pushing down because there's not as much atmosphere above. And so we see that the atmospheric pressure is quite a bit less than that. We actually can calculate some of these values as well. And so I actually looked up today to see what the atmospheric pressure was in Spokane. And so when I looked that up on one of the news stations, it said that it was 29.98 inches of mercury. Okay, inches of mercury. So if we want to know, so they're using barometer, but of course we oftentimes measure in standard in the US. So if we actually wanted to know what this was in all of the other units, well, we could convert our inches into centimeters. So we know that there's 2.54 centimeters in 1 inch. Okay, so I can do a conversion here. And when I do that, I end up with 76.15 centimeters of mercury, but I want to know millimeters of mercury before I can go on. So then what I can do is I can actually take that and I can multiply by 10, okay, to get centimeters. So by 10 is going to give me 761.5 millimeters of mercury. So that would be how many millimeters of mercury we would have for today's atmospheric pressure. Now I can actually convert this into the other two units as well. So if I take my 761.5 millimeters of mercury, okay, and I want to know how many atmospheres I have. For every one atmosphere, we said that was equal to 760 millimeters of mercury. Okay, so mm of Hg. Here we go. It's a little sloppy looking, but that's okay. And so that ends up being 1.002 atmospheres. And if I wanted to go a little bit further and I want to know what that would be in kilopascals, because kilopascals is actually the international unit, ATM. Okay, we know that for every 1 atmospheres, it's 101.3 kilopascals. Okay. And so that means that if we calculate that value out, we're going to end up with, it was 101.5 kilopascals. Okay? So that's just what we can actually find out for each one of these units, what it was in Spokane today. So just a little trivia for you. So we're going to take a look at a little further at some other things that we could be looking for as well. And so we know that we've already done some measurements this year with volume using liters or milliliters. We can also measure matter using grams, and then we can use those two things to find density, so mass divided by volume. And all of those things, and even more, are ways that we measure matter, but a lot of these are things that we're going to be using as we're working with different states of matter throughout this unit. Okay, so let's talk about the kinetic model of gases. And so we see gases here in this little cube, and it says that the particles are bouncing around. And that's exactly what's going on. So this is the fastest molecular motion, and it's the highest amount of energy. Okay, so I don't think it's the fastest energy, but the highest energy. Molecules are far apart and they have random motion, and we make a big assumption with these, and we make that assumption that there's no intermolecular forces of attraction between these particles. Okay, that's what we call an ideal gas. We'll talk about that a little more later. But we say that these things really aren't interacting with one another. They're just going crazy in the box. They're kind of like a mosh pit, and nobody's really paying attention to anybody else. So that's the dance style that we have here. The shape and the volume of this takes up the container. So you can imagine if you were maybe at some concert and you're in a very small venue, and the mosh pit's going to take over the entire space, where if you're maybe at a larger venue, it's going to spread out more. Okay, so as long as that's the only dance style going on there, they're all going to be going crazy. Right? So when we look at liquids are a little bit slower dance. So this might be, people are still just kind of swaying with the music, and everybody's kind of flowing together with the beat, but they're all kind of still separated. They might run into each other a little bit, but it's not quite as chaotic, but they're all a lot closer together. So we have medium molecular motion and kind of that middle ground of energy. Okay, they still have quite a bit of energy, but the molecules are far, far closer together, and they're freely flowing past one another. Okay, so everybody's kind of dancing. They might bump into each other, but they're going to kind of keep moving on in kind of fluid motion. And so we see a lot of intermolecular forces that might be happening at this point. We actually see that with solids as well, but we see that they're going to start to have interactions occurring between them. And these liquids take on the shape of their container, and so whatever container they're in, they're going to take on that shape, just like the gases, but they have a fixed volume. They kind of stay where they're not bouncing all over the place, but they're staying in one general location. So if we take a look at solids, we find that solids are really, really close together. And these guys, they kind of remind me of how my brother dances at a concert. He just kind of bobs his head back and forth and kind of moves just a little bit next to everybody. It always makes me kind of chuckle to watch him dance. So, or bob his head. So they're the slowest molecular motion. They're the lowest amount of energy. And we see that the molecules are close together. So they're all standing very close, and they kind of just move a little bit, kind of just shake a little bit next to one another, okay? There's a lot of interaction going on between these because they're so close together. So we see a lot of intermolecular forces because they're so tightly packed together. And once that happens, we can see two different things that will actually occur. One of them is crystalline solids, and that's where they're really orderly and fixed, and we can kind of see that here where it's really in a nice cube. We'll see some other things that are also called amorphous solids, and these are, they're not in this crystalline solid. So crystalline solids kind of tend to have this really fixed structure. These guys are going to be a little bit lacking in order, but they're still going to be tightly packed together, and just sitting there kind of shaking a little bit, okay? Maybe they aren't all exactly the same or set up exactly the same, but they're going to be very close together no matter what. And so what we see with solids is they have a very, very fixed, definite shape, and they also have a very fixed volume, okay? They are not going to spread out into everything else like the liquids did or the gases did. They're going to stay in their own little kind of group. And so that's what happens with each one of those. So we actually see another example of a crystalline solid here, okay, where we see this fixed network of things. And so that's really it. And as we actually add thermal energy or heat, or we see the temperature increases, we oftentimes go from a solid to a liquid to a gas. And so here we see that fixed volume and shape. Here we see the shape of the container, but we see that it's going to kind of have a fixed volume. And then here we see that it's going to take on the shape and the volume of its container. You can think about a balloon. As the balloon gets bigger, the gas particles will fill up that balloon. So that is a little bit about comparing the states of matter and a little bit about the kinetic molecular theory. I hope that was helpful.